Step into the Coliseum of Cambridge exams, where the clock is ticking, the pressure is crushing, and only the absolutely most prepared survive. Welcome to This Explainer. I am your host, and today we are conquering one of the most notoriously brutal, heavily weighted topics in the entire computer science syllabus: adding, editing, and deleting data, from stacks, queues, and linked lists. I want you to picture the exam hall. You turn the page, and there it is, a massive past paper question asking you to insert a node into an ordered linked list. It is high stakes. Now I want you to imagine two typical students facing this exact challenge. First, there's Alex. Alex is the kind of student who overloads his answer with raw computer science facts. He memorized the textbook, sure, but he provides absolutely zero analysis and zero logical flow. He tries to update his pointers in the exact wrong order, and he entirely breaks the linked list in memory. Data is lost forever. Then we have Sam. Sam just rushes. He completely misses the specific command word requirements, completely ignores the crucial edge case where the list might already be empty, and just draws a messy, incomplete diagram on the page. You can guess what happens next. Both of their answers are returned as a sea of red pen marks. They failed to survive the arena. Their mark potential dropped to zero. But here is the good news. By the end of this explainer, you are going to possess the exact step-by-step blueprint to avoid their fate and secure those top-tier marks. Now look at this incredible quote directly from the source. The examiner's warning here comes with absolute, non-negotiable certainty. This topic is completely unavoidable. The principal examiner reports explicitly state that this topic appears in every single examination series. You literally cannot hide from it, so we absolutely have to master it. And listen, mastering it doesn't just mean rote memorizing some code snippets. It means developing a deep intuitive understanding of the mechanics behind dynamic data structures. Think about what is actually happening under the hood. When you push data onto a stack, you are dealing with a strict last-in, first-out architecture. The last item in is the first one out. When you enqueue data into a circular queue, you are managing first-in, first-out logic, but it's more complex than that, right? You are actively calculating wrapping rear pointers so you don't run out of memory space. When you delete a node from a linked list, you are carefully, systematically rerouting pointers to bypass the deleted data without losing the entire rest of your data chain. The Cambridge examiners know exactly how complex this is, which is exactly why they test it so rigorously. They are hunting for the students who really get it.
So if you are currently tackling the Cambridge AS and A-Level Syllabus 9618, you need a precise, standardized system to survive. But let's be real. Even if you are currently building your foundations in the lower-level Cambridge syllabuses like 0417, 0478, 0983, 0984, or 2210, the logical thinking required here is exactly what you are building towards. The 96018 syllabus in particular is incredibly unforgiving. It demands that you not only write the algorithms, but that you physically trace them, evaluate their efficiency, and adapt them on the fly to completely unfamiliar real-world scenarios. You simply cannot walk into this coliseum hoping your basic foundational understanding of simple 1D arrays will somehow carry you through. It won't. You need a highly tactical strategy that specifically targets the exact method marks the Cambridge grading scheme is waiting to award you.
To get you there, we will follow this structured, 5-part playbook. This is exactly what top-performing students do differently. 1. Core theoretical principles. 2. The procedural framework. 3. The method mark strategy. 4. Top examiner warnings. And 5. Critical analysis mastery. Let's jump straight in. Section 1. Core theoretical principles, where we build your architecture of success from the ground up. Building that architecture requires a total mindset shift. You have to stop viewing stacks, queues, and linked lists as just abstract concepts and start viewing them as highly specific tools designed to solve specific data flow problems. This brings us to a concept that Cambridge specifically calls connected understanding. They want to see your ability to link precise definitions and causal relationships to unfamiliar contexts. And how do the top 1% of students achieve this analytical depth? They use the PEEL framework. That stands for point, evidence, explanation, and link. Let's say a 9618 exam question asks you to evaluate the use of a linked list versus a 1D array for implementing a dynamic queue. Your point is your initial clear argument. Your evidence is a hard technical fact. For example, the fact that linked lists use dynamic memory allocation. Your explanation details the why, how this dynamic allocation actively prevents memory wastage when the queue size fluctuates. And finally, your link ties it directly back to the highly specific scenario in the exam prompt. This perfectly maps out the causal relationship of the pointers and proves to the examiner you truly understand the concepts. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. click that subscribe button and hit the bell icon right now. You see, every single question in the Cambridge Coliseum targets one of these three distinct cognitive domains, so you must demonstrate mastery across all of them to survive. Knowledge and understanding is your base layer. Do you simply know that a stack uses a top pointer? Application of programming skills is the physical execution. Can you actually write the precise pseudocode to increment that top pointer while simultaneously checking for a fatal stack overflow? But analytical depth, that is where the absolute highest grades are born. This is your ability to trace a massively complex algorithm, find the hidden logic error in someone else's circular queue implementation, and entirely rewrite it for maximum efficiency. Section 2, the procedural framework. This is your tactical, standardized sequence for surviving the exam arena. Consider this your step-by-step combat tactic. Let's actively apply this systematically to the devastating mistakes Alex and Sam made earlier and watch those red pen marks transform into green check marks. Step 1. Deconstruct the question to find the exact command word. Are they asking you to describe, evaluate, or write the algorithm? Step 2. Extract relevant data. If the prompt explicitly gives you a pointer named top of stack, you must extract and use that exact variable name. Step 3. Select your analytical framework. Are you using the PEL structure for a written answer or an algorithmic sequence for code? Step 4. Execute with clear notation. This is exactly where Alex failed earlier. When adding a node to a linked list, you absolutely must link the new node to the rest of the list before you disconnect the previous node. If you cross those wires, the list is destroyed. Finally, step 5. Present with correct terminology. Do not say, the stack is empty and broken. Say, stack underflow. When Sam applied this exact 5-step framework, he realized his diagram lacked a boundary condition check, added his IF statement, and instantly secured full marks. The transformation is that simple. Now let's be honest, under real exam conditions, with the clock ticking, anxiety can completely wipe your memory. So I highly recommend using a visual story method to encode these abstract computer science concepts into a tangible, unforgettable narrative. For a stack, I want you to literally imagine a narrow tube of Pringles. You can only ever add a chip to the very top, that is your push operation. You can only ever eat the chip at the very top, that is your pop operation. If the tube is completely full, trying to jam another chip in just crushes it, that is a stack overflow. For a queue, picture a line for a roller coaster at a theme park. You join at the back, which is the rear pointer, and you eventually get on the ride from the front, which is the front pointer. FIFO logic. And for linked lists, imagine a complex treasure hunt. Each clue contains a piece of information, but crucially, it also contains the directions to the exact physical location of the next clue. If you lose just one clue, the whole rest of the treasure hunt is completely lost to you. Encoding these stories makes the logic unbreakable under pressure. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Section 3. The Method Mark Strategy. This is how you survive the arena, even when things go wrong. I want you to treat this like a data scan challenge. You have 60 seconds. Scan this chart. What is the core trend jumping out at you? Look at the massive, undeniable difference in exam mark potential between a student who hides their mental process and one who clearly displays their algorithm design. If you write a complex, 15-line pseudocode algorithm to enqueue an item, and you mess up the modulo arithmetic on the very last line, but you showed no comments, no logical structure, and messy indentation, the examiner might just give you a flat 0. But if you use crystal clear variable names, if you comment your steps, if you properly structure your if statements to check if the queue is full, and you clearly show your logical intent, you will capture the vast majority of the partial method marks. In Cambridge exams, the method you use to fight is often far more valuable than the final destination. I cannot stress this enough. Showing your systematic processing is exactly how you survive, even if you make a calculation error. Let's do a quick find the flaw challenge. I am going to read a flawed sample student paragraph, and I want you to spot exactly where they lose their marks. Listen closely. To delete an item from the queue, I will read the data at the front pointer. Then I will increment the front pointer to remove it. This completes the dequeue process.
I cannot stress this enough. Showing your systematic processing is exactly how you survive, even if you make a calculation error. Let's do a quick Find the Flaw challenge. I am going to read a flawed sample student paragraph, and I want you to spot exactly where they lose their marks. Listen closely. To delete an item from the queue, I will read the data at the front pointer. Then I will increment the front pointer to remove it. This completes the DQ process. Okay, time's up. Did you catch the fatal flaw? They completely forgot to check if the queue was already empty before trying to read the data. An examiner reading that will immediately dock marks, because in a real computer, that logic leads directly to an underflow crash. Always write out your boundary checks explicitly. Section 4. Top Examiner Warnings. Let's look at the exact fatal errors that trap unprepared students in the arena year after year. According to the examiners, these are the top 3 mistakes you must defend against. First, confusing cause and effect. Think back to our linked list. If you delete a node right in the middle of a linked list, you absolutely must update the previous node's pointer to point to the next node before you delete the current one. If you reverse that order, the chain is instantly broken. Second, forgetting boundary conditions. You must always ask yourself, what if this data structure is completely empty? What if it's completely full? Imagine I gave you a 30-second timer to write a perfect peel paragraph on this. Your point is that a queue overflow must be prevented. Your evidence is that the array size is physically limited. Your explanation is that adding data overwrites existing vital memory if it's full. And your link is that an IF statement checking if rear equals max size must precede any insertion. That is how you fix those fatal flaws in record time.
The third fatal flaw is lacking specific context. This exact examiner feedback proves that simply reciting generic textbook facts about queues or stacks will absolutely not earn you top grades in 9618. For instance, if the exam prompt is heavily focused on a stack being used to track the undo operations in a custom word processor, and your written answer just talks about generic data items, you will lose those crucial context marks. You need to adapt. You need to say, when the user clicks undo, the previous text state is popped from the stack. You must mold your technical knowledge to their highly specific scenario.
Section 5. Critical Analysis Mastery. This is where we achieve true analytical depth. Top-tier Cambridge answers don't just list facts. They compare approaches and evaluate alternatives with rigorous, justified recommendations. Look at this comparison right here. Superficial breadth is writing something like, both arrays and linked lists can store data queues. It's true, but it is incredibly shallow. Analytical depth, however, identifies similarities and differences using what we call comparative connectives. Listen to the difference. Whereas a static array requires a fixed block of sequential memory, a linked list allocates memory dynamically for each new node. Consequently, the linked list is far more memory efficient for a wildly fluctuating queue. Notice those powerful words like whereas and consequently? Using those words forces your brain to physically justify your technical statements with evidence. If you can actively deploy these higher-order assessment objectives under pressure, you demonstrate true, undeniable mastery. So let's bring all of our strategies together into one complete, unbreakable answering system. The 3 rules that guarantee top marks. Rule 1, command word decoding. Know exactly what evaluate, describe, or write demands of you before you pick up your pen. Rule 2, Peel framework application. Never, ever write a paragraph without point, evidence, explanation, and link. Rule 3, the time management matrix. Do not rush through a massive 8-mark algorithm design without mapping your logic and your boundary checks first. Evaluating alternatives and making justified recommendations is the absolute playbook of a gladiator who has mastered the Cambridge system. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. So as we wrap up this explainer, I want you to take a serious moment to evaluate your own study habits. Are you just memorizing pseudocode out of a textbook, crossing your fingers and hoping the exact same question appears on your paper? Or are you actively building a flexible, dynamic system of thought that can adapt to literally any unfamiliar context they throw at you? Because I promise you, the examiner's method is the only method that actually awards the marks. Master the method and you master the arena. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.